In this lecture, we present the basic notions of stability of equilibrium points. We will define stability, instability, asymptotic stability, and exponential stability of an equilibrium point. We will also explain the difference between local and global stability. Stability theory plays an important role in engineering, so it's important for an engineer to understand different notions of stability. The stability definitions presented in this lecture are for nonlinear time invariant systems in the form of x dot equals f of x. Definitions for nonlinear time varying systems x dot equals f of t and x are slightly different and will not be covered in this video. For the stability analysis, it's common to assume that an equilibrium is located at the origin. So without loss of generality, we also assume when studying the stability of a system that the system has an equilibrium at the origin, that's xe equals 0, where the dimension of the system is n. If this is not the case for a system, the equilibrium point can be shifted to the origin by a change of variables. As an example, consider the first order system and note that it has one equilibrium point. The equilibrium point can be found by letting x naught be 0. If you don't know what an equilibrium point is or want to learn more about equilibrium points, watch the video linked below. In this example, the equilibrium is at -1 and we want to shift it to the origin. We define a new variable x bar equals x plus 1. Notice that x dot equals x bar dots. Then by substituting x by x bar minus 1, we can rewrite the system model as x bar dot equals 2x bar. The equilibrium point of the new system is at the origin. This can be checked by setting x bar dots to be 0 and obtaining that the equilibrium in the x bar coordinates is at the origin, which is x bar e equals 0. We are now ready to define the first stability notion, which is the stability in the sense of Lyapunov, or simply the stability. Roughly speaking, the origin is a stable equilibrium in the sense of Lyapunov, or simply is a stable equilibrium if all solutions starting at nearby points stay nearby. Otherwise, it's an unstable equilibrium. For example, consider a system with two state variables x1 and x2 and an equilibrium at the origin. This system is stable if all solutions starting near the origin stay near the origin for all time. An example solution is shown in this figure. Note that the solution doesn't need to tend to the origin. It only needs to stay near the origin. We can now propose a more technical definition of stability. The origin is a stable equilibrium in the sense of Lyapunov, or simply is a stable equilibrium of x dot equals f of x, if for each positive epsilon, there exists a positive delta such that norm of x of 0 less than delta implies that norm of x of t is less than epsilon for all time. To clarify this definition, we will illustrate the concept of stability for a two-dimensional system. The equilibrium point at the origin is stable if for each ball with radius epsilon centered at the origin, there exists another ball with radius delta centered at the origin, such that all solutions of the system starting within the delta neighborhood of the origin stay for all time within the epsilon neighborhood of the origin. In other words, if a system is stable, you can decide how close you want the solutions to remain to the origin, and it's always possible to find the neighborhood of the origin from which the solutions start and remain for all time within the neighborhood you chose. So it's always possible for a stable equilibrium to find a set of initial conditions such that the solutions stay as close to the origin as you want for all time. We emphasize again that the stability definition in the sense of Lyapunov doesn't imply that solutions converge to the origin. Also, as can be seen in the definition, the value of delta depends on epsilon. Finally, delta is not unique. For any delta that satisfies the condition of the definition, any delta prime less than or equal to delta also satisfies the condition. As an example, consider a harmonic oscillator with a state model represented as x1 dot equals x2 and x2 dot equals minus x1. The equilibrium point of this system is x1 equals x2 equals 0, and the solutions starting from the initial conditions x1 of 0 and x2 of 0 are x1 of t and x2 of t as shown here. It can be observed that the norm of the solutions is equal to the norm of the vector of initial conditions. This means that solutions of the system are all circles with radius equals to the norm of the vector of initial condition centered at the origin. So for any given initial condition, the solution is a circle centered at the origin. This figure illustrates the solutions of the system from several initial conditions. Note that the origin is an equilibrium point. So if we start from the origin, we will stay at the origin forever. Let's now use the stability definition and show that the origin is stable. Given any positive epsilon, we want to find delta such that all solutions starting in the ball with radius delta remain in the ball with radius epsilon. So in this example, delta can take any positive value which is less than or equal to epsilon. Since for any given epsilon, we can choose delta less than or equal to epsilon, the origin is a stable equilibrium in the sense of Lyapunov. We now go to the second definition, which is instability of an equilibrium point. The origin is unstable if it's not stable. This means there exists a positive epsilon for which no positive delta can be found such that norm of x of 0 less than delta implies norm of x of t is less than epsilon for all time. Let's study a simple example. Consider a first-order system x dot equals x, and note that this system has one equilibrium point at the origin. The solutions of this system, starting from the initial condition x of 0, are in the form of x of t equals x of 0 times e to the t. So all solutions of this system, except the solution starting at the origin, which is the equilibrium point of the system, grow unbounded. This figure illustrates some of the solutions of this system, including the solution starting from the origin. We now use the definition to show the origin is unstable. We choose a positive epsilon and see that there is no neighborhood of the origin from which the solutions start and remain within the epsilon neighborhood. So this means that the origin is unstable. We now define the next stability notion, which is asymptotic stability. The origin is an asymptotically stable equilibrium if two conditions hold. Firstly, if the origin is stable, and secondly, if the origin is attractive, which means that limit of x of t when t goes to infinity is equal to 0. As an example, consider a nonlinear system x dot equals minus sine of x. To calculate the equilibrium points, we set sine of x equals 0 and obtain that x equals kp, where k is an integer. We then use MATLAB and plot some of the solutions of the system to see the behavior of the system near its equilibrium points. An equilibrium is asymptotically stable if all solutions starting at nearby points not only stay nearby, but also tend to the equilibrium point as time approaches infinity. It can be seen that the origin is stable and is also attractive, as the solutions starting near the origin converge to it as time goes to infinity. So we conclude that the origin is asymptotically stable. We finally define the last stability notion, which is exponential stability. The origin is exponentially stable if there exist positive constants delta, alpha, and beta, such that norm of x of 0 less than delta implies that norm of x of t is less than alpha times norm of x of 0 times e to the power of minus beta t for all time. We see from the norm of x of t inequality that as t approaches infinity, the norm of x of t goes to 0, which means that x of t goes to the origin. So if an equilibrium point is exponentially stable, it's asymptotically stable and also stable. A simple example is a linear time invariant system x dot equals minus x. It has an equilibrium at the origin, and the solution starting from x of 0 is x of t equals x of 0 times e to the minus t. It can be seen that the solutions satisfy the condition of the definition with alpha and beta equal 1. We could also choose other values for alpha and beta. For example, we could choose alpha equals 5 and beta equals 0.2, and the condition in the definition holds as the norm of x of t is less than or equal to 5 times norm of x of 0 times e to the power of minus 0.2t. As you see in this example, the exponential function that upper bounds x of t is not unique. We have defined all the stability notions that we will use later when analyzing and designing controllers for nonlinear systems. It's important to note that all the stability definitions we studied so far are local, which means they only give us information about the behavior of an equilibrium when we are around the equilibrium. But there is no guarantee that, for example, for all initial conditions in the space, the solutions tend to the equilibrium and therefore the equilibrium is globally asymptotically stable. We now propose conditions for global stability and start with global asymptotic stability. The origin is a globally asymptotically stable equilibrium if it's stable and if it's globally attractive. This means that the limit of x of t when t approaches infinity is equal to 0 for all x of 0 in Rn and not only for initial conditions in the neighborhood of the equilibrium. Similarly, the origin is globally exponentially stable if there exist positive constants alpha and beta such that norm of x of t is less than alpha times norm of x of 0 times e to the power of minus beta t for all time and for all initial conditions. As a final comment, note that we usually don't use these definitions to check if a system is stable or not. We will learn tools such as linearization technique or the basic theorems of Lyapunov's method to determine if a nonlinear system is stable, asymptotically stable, exponentially stable, or unstable. The aim of this lecture was mainly to understand the meaning of different stability notions.